Hello everyone, and welcome to the c-cubed channel. Welcome to c-squared extras. In this little side series, I'll be covering some details and some topics that I talk about on my main channel, c-squared, but in more detail. So you can expect a lot more maths, a lot more crazy derivations, a lot more concepts, and everything that I wouldn't really put in my main channel. So this is more for those who want to have a better understanding of what I'm talking about on the main channel and want more, in-depth knowledge as to what's going on. So what this video is today is we're going to be talking about the transmission probability for one particle to pass through a barrier. Now, this might sound familiar. This is coming from the recent video I did on my main channel, c-squared, which was, could you walk through a wall? But that is the video that I talked about there. And so what we're going to do in this video is I'm actually going to show off the model that I created. I'm also going to show off the derivation of how you can get to the values that I got in the main video. What we need to begin with is we need to begin with the initial setup, as we have talked about in the main channel. So we have this image here. If you might remember this from the main channel. We have a particle that is on the left side of the graph here, and the energy is less than the height of a barrier that is on the right side of the graph. So that's the setup. We want to find out the probability for this one electron to pass through to the other side of this barrier with width of d. Now we want to find out the equation that can tell us this, and we also want to find out how we can use this to get a more macroscopic level, so it's for like humans, and we also need to see what happens if you have multiple particles. So we're going to start with some assumptions here. Obviously, this is going to carry on throughout the whole derivation, but the assumptions here are that all particles in the average human body will be regarded as electrons, and all their energies will always be below the potential barrier. So at this point, E will always be less than V at all times. So the energy needed to overcome the barrier remains the same in all cases, regardless of the thickness of the barrier. And the distance particles tunnel through is D, and this will be the average thickness of the UK house wall. So in this case, we'll make D equal to 23 centimeters. And another thing is all the particles in this case will be moving in a 1D motion, so they will only be moving in positive x direction. So that's explained in this graph right here anyway. Another thing is all the particles in the average human body will interact with the barrier at the same time. So that means that we're gonna disregard the fact that the human body is three-dimensional, and we're gonna have kind of, I guess you could say, a sheet of particles that collide with the barrier all at once. Now, that will make calculations much easier, because everything will be instantaneous, instead of having the problem where maybe the front part of your body will tunnel through, but the back part won't. Cases like that, which are a lot more complicated. But for the sake of simplicity, for the sake of this video, and for the sake of my c-squared video, we're just gonna use that assumption. And one last thing is the external forces and the interactions between the particles themselves are completely ignored. So we're not going to take those into account at all. So with all those assumptions in mind, we can begin the derivation for this situation here. We're going to see what the probability is to walk through a wall. To begin, we're going to start simple. We're going to start with one electron only. Alright? So the electron is on the left side of this barrier here, as we've already said. It needs to cross to the other end, but the energy will always be less than the barrier height. The first thing we need to do is we have to find a way to describe the electron in each of the three situations. So we can split this graph into three different sections. Region 1 will be on the left of, the leftmost portion of the graph. Region 2 is the portion where the barrier occupies it. And then region 3 is on the far right. So region 3 is basically the area after the barrier. We have to take into account what happens to the electron at all three regions. So we can describe the electron as a wave, and that is because of wave-particle duality. And so what we can do is we can find what is known as a wave function. Now, a wave function is, well, this will basically be the mathematical description of an electron that moves throughout the barrier, the potential barrier at this point. So, because of wave-particle duality, we can represent a particle, in this case the electron, we can represent it as a wave. And we can see the description as it passes through the three regions. And for each of these cases, we're going to use the one-dimensional Schrödinger's time-independent equation, which is this right here. So to quickly break this down, the first term here, this is the kinetic energy portion. The second one is the potential energy portion. And the last one is the total energy portion. So if we were to take this into a more classical approach, then you could kind of see this is very resembling, what happens with macroscopic scales with classical Newtonian mechanics, where you have kinetic energy plus potential energy will give you the total energy. That is the same in this case, but just down to, quantum scales. So what we're going to do now, we're going to take this equation here, and we're going to apply it to the three regions I was talking about earlier. So we're going to have three different wave functions, essentially. We're going to be seeing how the electron can be described in each region. So let's begin with region 1, which is on the leftmost side of the graph. This is electron just freely moving up until the central potential barrier point. So in this case, what happens here is that the electron is sitting in an open region. There is no extra energy here, because there's no barrier. In this case, the u of x term is equal to 0. So this middle portion here will completely vanish. And we are now left with this differential equation right here. If we do some quick rearranging, we can get it in this form, which is a lot neater. And we can also make a substitution. We have to make use of what is known as the wave number, and that will make that k. So in this case, k is equal to square root of 2me over h bar. And we can see from the equation there, the second order differential equation, we have a form of k already in there. So we could just make the substitution as k squared. And so we get this equation here. We rearrange it once more to get this. And now we can just solve this simple second order differential equation. And when you solve it, you should get this answer as the wave function. Now, I should note that there are two terms here, and both are added together because, due to the fact of Heisenberg's uncertainty principle, we don't actually know where the electron could be at any point in time, as I've mentioned in the main video. We also don't know what direction the electron could be traveling in. So, in this case, we simply just add them together. So we superpose the results. So that was all we get for region number 1. And that's the answer for that. That's how we can describe the wave function for the electron in the first region. That's how it looks in a waveform. Now for region number 3, which is over on the far right side beyond the barrier, again, in this case, the u of x term is equal to 0 beyond the region. So again, this is exactly the same situation as in region 1. So we just, we're just going to skip all the steps and jump straight to the answer because it's the same derivation. The wave function for the third region is given by this here, which is equivalent to what we had earlier. In this case, the difference here is that the particles beyond the barrier can actually extend on towards infinity. They will never really reach another barrier at this point. So we can actually consider the h term here, the second one there, to be 0. And because of that, we're just left with that equation right there. So now we have these two wave functions for both regions 1 and 3. And now we need to find out what's going on in the middle of the plot. We need to see what's happening with the barrier. So for region number 2, in this case, the electron is inside the barrier now, because E is less than V. So, what we do here, once again, we begin with the 1D Schrödinger equation. However, u of x is actually not 0, and it is in fact equal to V. So now we have to consider that middle term. Now the equation will be this. So we're going to rearrange again, we're going to do what we did before, and we can get this equation now. In this case, we have a new type of wave number, which I'll use capital K for, and K squared here in this case would be 2m e minus v now over h bar squared. And of course we rearrange it again, put it back in, rearrange, we get our we got a typical second order differential equation as we had before. And now we solve. So by solving this equation, we now have the new wave function for the middle portion of the barrier. And in this case, we have a different wave number than we did before. We need to do one more thing. Right now, this wave function right here is not a real function. And we have to convert it into that so that we can, get into, we do that so that we can actually get to the tunneling equations that we need later on. So we do that with a very simple substitution. We use capital K is equal to I alpha. I obviously is, the imaginary number. I is equal to the square root of minus 1. And so in this case, we take it such that alpha is equal to K over I. And of course, we can just substitute what K is, and we get what do we know there. With that substitution done in mind, we have now transformed the equation in terms of alpha. So that is our second wave function. So now we have all three wave functions together. We have the wave function for the leftmost portion, we have the one for the middle region, where the barrier is, and we have one for the rightmost portion, which is extending beyond the barrier. It is time to go on with figuring out what the probability is for one electron to tunnel through a barrier. Now there's a lot of arbitrary constants here. There are in fact 5 right now, so we need to start getting rid of a lot of them. Now the main one we have here, the main one of interest we have here, is g, so that's over on the third wave function, because this is related to the wave function of electrons that emerge after the barrier. And in that case, this describes electrons that have actually managed to tunnel through the barrier. So g, the arbitrary constant here, will give us a good idea on telling us what the probability of the electron tunneling through will be. And of course, this relationship here of knowing what g is and such, it will also lead us to what is known as the transmission coefficient, which I'll get to later. In order to get this value, we have to take the ratio of g over a, which is taken from the third wave function and the first wave function. So this is looking at the ratio between electrons that make it after the barrier with those that make it before, so that we can see kind of the transmission coefficients and such. I mean, that ratio involves a lot of algebra hell, so the maths behind that is a complete nightmare, and there, it's a mess. So to save you guys the trouble, I'm gonna jump ahead straight to the answer of that ratio with the approximations done and everything. And what we get in the end is we get this value of the ratio, which is taken from all three wave functions together. That's after doing multiple cancellations and such. And the modulus of this is taken as that. So of course, we're just going to see the magnitude of this ratio. Now using this, we can find the transmission coefficient t. And that is done by squaring both the modulus of g and the modulus of a, and then finding the ratio between them, which is given by that. And so when you solve that, we will get this value. So this is the probability for one electron to tunnel through a potential barrier with width d. Now we can approximate this a little bit further if the wave number k and alpha are of the same order of magnitude. So basically if they're kind of, at the same nanoscopic scale and such. In that case, we can actually cancel them away from each other, and all we're left with in the end is we are left with this, which is that t is equal to 4e to the minus 2 alpha d, where e is the exponential function, of course. Alpha is given by that wave number right there. Well, the real wave number, I should say. And there we are. That is the probability of one electron with energy E to tunnel through a potential barrier with D and energy V. What we have here works for quantum scales, so the width of the barrier has to be comparable with what is known as the de Broglie wavelength. So that's the wavelength of a particle that can be described as a wave. So in this case, the width has to be in and around the same kind of length as the de Broglie wavelength in order for this to work out quite well. Let's test this quickly with the quantum scale. So the average mass of an electron is given by that. Now we're going to throw random numbers here, just for the sake of the scale we're working at. And let's say the potential energy needed to overcome the barrier is 5 electron volts. And the energy of the electron is at 0.5 electron volts. In this case, the width of the wall will be 0.01 nanometers. So, by putting all of these values together, we get this huge block of stuff right here. So obviously we're just plugging all the numbers in, we're substituting alpha back into it, and we're going to put all the numbers in, and we could get our transmission probability of 0.46, which I have actually mentioned in my main video with working at quantum scales. So we can see here that almost 50% of the time the electron will suddenly tunnel through to the other side of the barrier, and this is quantum tunneling in practice. So now let's jump up to the human scale, which is what the main interest of the original video is and what the derivation here is for. The only thing that's going to change here is the thickness of the wall, which will be increased to 23 centimeters, as the average thickness of a UK house wall. So if we do the exact same calculations with everything else there, except for the width now being 23 centimeters, this results in a dramatic change than what we had with 0.01 nanometers. Now we can see that the transmission coefficient is that tiny number. Now remember that the electron has to tunnel through the entirety of the 23 centimeter length. So with such a massive scale like this, the probability is pretty much almost zero. But note that it is actually still probable. To get the idea of the scale where we're at here, I tried to convert this value into just an ordinary number to see how many zeros you could get from this, how many decimal places you'd need. I've used a few places, and what I found was the number either just rounded down to zero, it couldn't convert it very well, or it just completely broke the calculator and didn't understand what I was talking about. So if it wasn't clear enough, yeah, this is very small. Now, we'll be answering the question that the main video was built on, which is, what if we want all the particles in our body to tunnel through a wall? Let us say that the average human body has about 7 times 10 to the 27 particles, or in this case, we'll regard them all as electrons. As I've done in the main video, I talked about this as well. Using the same conditions as before, we know that the probability for one electron to pass through a 23 centimeter wall is that beast of a number, and we need to consider this for this many electrons. Now we're going to be using what is known as the binomial distribution here, which is kind of a simplified model that I'm doing right now. Of course, the binomial distribution in this case, I'm going to be taking the n, which is the number of trials, will be all of the atoms, or all of the electrons in this case, in the body, so 7 times 10 to the power 27 would be our n. And then the probability, p, for the distribution model, it would be the probability for one successful electron to pass through the barrier in its entirety. So the binomial distribution model is being made as this. Okay, cool. So in order to find the probability of success for all 7 times 10 to the 27 electrons, we just simply do p to the power of n, which in this case we can see is this number here. Now, this value cannot be computed, of course, but I estimate that this corresponds to a decimal value where you would have at least several hundreds, if not thousands of zeros before you get to your first non-zero number. So this is basically, well, as I've mentioned in the main video, you can probably tell by now, this is the probability of walking through a wall using this simple model that I've created. Now, of course, I've made a lot of assumptions here, and the calculations are very far from being accurate and perfect, but ultimately what I want to get at is the scale of such numbers here, rather than any exact values. What this shows, though, is that even at a human scale, there is still a chance for a person to completely tunnel through a wall using quantum mechanics principles. But such a chance is so tiny you could pretty much say it's zero at this point and just resort to using classical physics for such large-scale objects like this. Of course, you cannot actually rule it out completely, though, because you can't actually apply quantum principles to human-scale objects. It's just the probabilities of such things are going to be pretty much always almost zero, so there's no real point in mess around with them, but it is something cool to consider, I say. Now, if you did want to tunnel through, my guess is, as I mentioned in the main video, you'd probably take well longer than the current age of the universe in order to get a decent chance of phasing through a wall. So, if you want to get started, then well, I mean, you can sure go ahead, but I wouldn't recommend it. So, that is all I had to say on this. Thank you guys so much for watching this extra content. I hope you kind of have an understanding of where I got these values from. And I'll see you all back on the main channel.